Now, we talked about dynamical systems earlier, right? We have these problems with some initial state, and then xn would be some future state. After n, we'll call them days. It may not be days, it might be hours or minutes or whatever the case is. And then you have a dynamical system where the future state is related to a previous state by a very simple update equation. Eigenvector basis allows us to see far into the future with little work. Now, as an example of this, if I tell you, okay, here's a matrix that characterizes a dynamical system, and I'm not going to worry about the background behind it, it will turn out that it has an eigenvector basis. So the eigenvectors in this particular problem would be 3, 5, and 1, negative 1. The eigenvalues that are associated with it would be 1 and 0.92. Because these two vectors live in R2 and they are not multiples, they will be sufficiently different enough to be independent and to span. We are going to take some initial state of our problem, and because we have a basis, we would love to figure out what the basis representation of this initial state. We want to know what the weights are, the coordinates in that basis. So that means we have to solve the system V1, V2 is this x naught. You do a bit of row reduction, what you're going to find is that you'll get 0.125, 0.225. But the point of the story is this vector, which has this standard basis representation, is 0.125 V1 and 0.225 V2. So if we want to know the state of our system after 1 day, we calculate this. If we want to know the state of the system after 2 days, we calculate this. But from above, we know that that result is true. So it will turn out that x2, you'll need a square power of that matrix. If you generalize this, I'm hoping that you can see if you want to calculate to some arbitrary day after the initial, you need to calculate that. Now, this becomes easy when you are in the right basis. For example, x1 would just be a times x naught. Well, x naught was 0.125 v1, 0.225 v2. By linearity, this is 0.125 AV1, 0.225 AV2. That's the goal. We want to get AV1 because these are eigenvectors. And because they're eigenvectors, you're allowed to replace the AV1 with its appropriate stretching. So it's 0.125. And then we need the first eigenvalue. Well, the first eigenvalue was 1, 0.225 times 0.92, which was the second eigenvalue, times V2. x2 was a times x1. Well, now we just repeat this game. 0.125 V1, we take our answer from above, and we plug it in, and we use linearity again. Linearity is an extremely important property. If you haven't gotten it by now, now's your chance. You need to get it straight now. Why do we want linearity? Because by definition, this matrix has some preferred directions built into it. This eigenvector and value ends up giving me a 0.92 squared V2. So I'm hoping that you can see after a very long time, what's going to end up happening is that we'll get this type of result. So in the future, long in the future, n will go to infinity, and that means 0.92 to the power of n will go to 0. In the future, I can tell you exactly what this system is going to do. This system is going to approach 0.125 bunches of V1. That is what we'll call the steady state of this system. That's the solution that this system will converge to. So because of this eigenvalue and eigenvector machinery, we have been able to solve a long-term problem relatively straightforwardly.